Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the BSc Physical Sciences students. We have been discussing about the vector atom model in the unit 2, then the spatial quantization, electron spin, and the quantum numbers associated with the vector atom model. This is one of the very important lectures in the sense, look at the last line, the electronic configuration of atoms, or in other words, the Mendeleev periodic table is explained based on the vector atom model in conjunction with the most famous Pauli's exclusion principle. So, the contents of this lecture are quantum numbers associated with the vector atom model, Pauli's exclusion principle, electronic configuration in atoms. In continuation to what I have been telling you in the last lecture, you come across in the vector atom model the quantum numbers n, l, s, j. Then in addition to those quantum numbers which you get when you do not apply any field, or when you do not apply any magnetic field especially, and now you apply a field so that you want to have a reference direction, and again when do you apply the magnetic field? To explain Zeeman effect or to explain Stark effect, you apply electric field. Therefore, in the presence of a magnetic field, you will come across additional quantum numbers such as ml, that is a magnetic orbital quantum number, that will have 2l plus 1 values ranging from minus l to plus l, obviously including 0. That is, they are the ml values. ml is called the magnetic orbital quantum number. Similarly, you will be having the magnetic spin quantum number. So, the magnetic spin quantum number ms, again similar to ml, will have 2s plus 1 values starting from minus s to plus s. Minus s means minus of, plus s means plus of. So, there are the only 2 possible values that ms can take if s is equal to half. Suppose it takes some other value, then of course, you go to mj, the total magnetic quantum number mj, similar to ml and ms. mj will also take 2l plus 2j plus 1 values. These things we discussed to a certain extent in the last lecture. 2j plus 1 values are ranging from minus j to plus j excluding 0, because your j is sum of l and s, this half will be coming, therefore, 0 will be absent in the case of mg. Okay. Therefore, once again I will tell you there are 7 quantum numbers n, l, s, j, and then there are projections of ML, MS, Fg. Okay. Then comes the Pauli exclusion principle. It is a quantum mechanical principle which says that out of the 7 quantum numbers, at least 4 of them are required to distinguish one electron from the remaining electrons in an atom. Let us take an atom like carbon or sodium, got 11 electrons. You cannot, all the 11 electrons will not have the same quantum numbers, or you should be able to distinguish one electron from the remaining electrons. You know, when you go to the passport office, you are asked to give some identification marks, similar to a mole on the left cheek or something on the right hand. They are the marks which are used to distinguish one person from the other person, or nowadays you have got more sophisticated ways in the passport office, similar to the case of what is being done to distinguish one man from the other man. In the case of electrons also, to distinguish one electron from the rest of the electrons in an atom, say like sodium got 11 electrons. So, to distinguish one electron from the remaining other electrons, you require how many quantum numbers? According to Linus, according to Pauli, Wolfgang Pauli, you require 4 electrons, namely N, L, Ml, Ms. Okay. You require 4 electrons to distinguish each and every electron in any given atom. Every electron you should assign 4 quantum numbers to describe a particular electron. So, namely the quantum numbers which are required are N, L, Ml, Ms. We were talking about 7 quantum numbers. Out of 7, at least 4 are required to distinguish one electron from the remaining electrons. You will understand what I mean by this in the time to come. So, according to Pauli principle, every completely defined quantum state in an atom can be occupied only by one electron. What do you mean completely? What do you mean by quantum state? When you have a set of values N, L, Ml, Ms for a particular electron, that is a quantum state. No other electron in the atom can have the same set of quantum numbers. Again, I will tell you, when I am talking about N, L, Ml, Ms, there can be only one particular set. When you talk of some other set, at least one number should be different. Very often it is wrongly stated by many students. The point I want to tell is the Pauli principle states no 2 electrons can have the same set of quantum numbers. Sometimes we find the word set is missing. That is misleading, wrong. No 2 electrons can have the same set of quantum numbers. Suppose I assign N is 1, say L is 0, Ml is what? L is 0 means Ml will be 0. Ms will have plus of. Again, for another electron also, you should not have 1, 0, 0 plus of. That is first state 1, 0, 0 plus of is one quantum state. Then the next should be 1, 0, 0 what? Minus of. You cannot have plus of. One of the numbers should be different. Either N should be different, should have different value, or L should have different value. You will understand more in the time to come. So, let me now continue. In other words, it is impossible for 2 electrons in an atom to be identical as regard to all the quantum numbers. All the 4 quantum numbers should not be identical. It is variously stated no 2 electrons in an atom can occupy the same quantum state, or as no 2 electrons in an atom can have the same 4 quantum numbers. All the 4 quantum numbers N, L, Ml should not be identical for the electrons in an atom. The exclusion principle explains certain experimental observations such as the occurrence of or non-occurrence of spectral lines, and the scheme and the arrangement of electrons and atoms. The most important thing is the arrangement of electrons and atoms is properly described in today's understanding. How many electrons you can have in the first shell, or how many you can have in the second shell, or how many you can have in the 3 subshells in the third main shell. The third main shell will have 3 subshells, and the second main shell will have 2 subshells. How many you can have in each and every subshell, and how many electrons you can have in a main shell. These things come from the vector atom model, but in conjunction with the Pauli principle. You have to apply the Pauli principle. The vector atom model provided a rational explanation or of several complex atomic and spectral phenomena. Out of them, the most important are the electronic structure of atoms. That is what I told you. The electronic structure, that means how the atoms are, how the electrons are arranged in atoms. In the first shell, how many electrons you have got? In the second, how many you have got? Third, how many? Suppose you have got an atom like lithium, you have got 3 electrons. Can I put all the 3 electrons in the first shell? It is not possible. You know, even in high school, you write 1s2, 2s1. These things come from the vector atom model along with the Pauli principle. In conjunction with the Pauli principle, you are able to write the electronic configuration or electronic structure of atoms, or electronic configuration is written based on the quantum numbers that you make use of in the vector atom model in conjunction with the Pauli principle. So, not only the electronic structure of atoms are described with these principles, but also the Zeeman effect, the anomalous Zeeman effect, and the Stark effect. So, the vector atom model has been highly successful, and let me now pass on to find out and explain to you as to how many electrons you can have in a subshell, main shell, and so on. The electron in an atom will occupy energy or orbitals characterized by quantum numbers n, l, ml, ms. I mean by energy, in the Bohr atom model, the energy of the electron depends upon 13.6 divided by n square. So, n decides the energy levels in the Bohr atom model. Similarly, here these numbers will also decide the orbits and also the energy levels. That is what I am telling here. A set of these numbers defines the quantum state of the electron. The states or orbitals are organized into subshells, and finally in main shells, the possible orbitals corresponding to a particular value of n are said to constitute a shell. In a shell means I will finally explain to you or express the number of electrons in terms of n. That is what I am telling here. A particular value of n, the K shell will have so many electrons given in terms of n. L shell also will be given, the number of electrons the L shell also will be given in terms of n. That is what I am trying to tell you from this line. All the electrons in an atom which have the same principal quantum number n belong to that particular electronic shell. That is, the K shell will have n equal to 1. The L shell will have, n equal to 1 means that the K shell, n equal to 2 means that the L shell, and so on, right. K, L, M, N, O, P, they are the main shells. All of you have studied in high school, for which the n values are 1, 2, 3, etc. right. Remember, n takes a value 1 means that the K shell, the electron is the first shell. Then the remaining electrons will go to the next shell. When I say remaining means, what do you mean by remaining? The remaining electrons, that is coming from the Pauli principle. Pauli principle says that in this house or in this shell, you can have only so many electrons. If you exceed that, you are violating the Pauli principle. Therefore, Pauli principle lays restrictions on the number of electrons you can have in a given subshell or a main shell. These things you have to understand. We will go through these things in detail now. Let us have a break at this point. Welcome back at the break. We have been trying to understand as to how many electrons you can have in a subshell as well as a main shell. This we try to understand based on the quantum numbers we have come across in the vector atom model, but of course definitely in conjunction with the Pauli principle or the restriction that a Pauli principle enforces on the quantum numbers or the quantum states. All the electrons in the atom which have the same principal quantum number will have a particular n value, it is obvious. The electron, the first shell, the K shell, the second shell is called a L shell. The designations or these things you have studied in school. The principal quantum number is given by n. They take values like 1, 2, 3, etc. They are designated like K shell, L shell, M shell and so on. A shell is characterized by the principal quantum number n, and it accommodates a maximum number of electrons which goes as 2n square. That is what I told you a bit earlier also. The number of electrons in a main shell depends upon the n value. I am giving the answer much earlier in the sense before asking certain questions. How do you arrive at this relation? They are a very important relation. The relation says, the line says that the number of electrons you can have in any given shell, n refers to any shell, n is 1 means the K shell, n is 2 means the L shell and so on. In any given main shell, the total number of electrons which could be accommodated is given by the expression 2n square. Now apply this for the first shell for which K shell, that is n is 1. So how many electrons you can have in the first shell? You can have 2 into 1 square, 2. How many you can have in the second shell? 2 into, you can have n is 2, right? The second shell will have 2 square, that means 4, 2 into 4, 8. Take the case of sodium. How many electrons you can have? You have got 11 electrons. So how many you will have in the first shell? I told you the first shell can accommodate only 2 electrons, because for the first shell n is equal to 1. 2n square, 2, okay. Out of 11, you have driven 2. 2 have gone to the first shell. Now how many are remaining? 9. How many you can put in the second shell? The second shell, as I told you, for the second shell n is equal to 2. So 2n square means what? 2 into 2 square, that is 8. So put 8 electrons in the second shell. So you write the first shell will have 2 electrons, the second will have 8 electrons, the 11th electron of sodium should obviously go to the third shell. That is the reason why you write in the high school 3s1, right? The electron, the outermost electron of sodium will go to the third shell, and the first subshell which is designated by the letter S. We will talk about a subshell now, okay. So the value of n increases as the distance of the shell from the nucleus increases, because the K shell, L shell and so on, okay. So obviously these things will occur, and the K shell with n equal to 1 will accommodate 2 electrons, L will accommodate 8 electrons and so on, okay. So the number of electrons you can have is 2, 8, 18, 32, 50 and so on, okay. You have 2n square, right? N equal to 1, 2 into 1 square, n is 2, 2 into 2 square, as I told you 8, then 18, then you have got n value, right? 2 into 16, that is 4 square is 16, 32, and therefore the number of electrons you can have in any main shell is given by the expression of this kind. The numerical values are given here. Then we have to talk about subshells also, okay. The shells are built from subshells which are designated by the letter L. The letter L will be the K shell, let us take. It has got the main shell and the subshell are one and the same. There is only one shell. N equal to 1 means you have got the subshell and the main shell are the same. Whereas you go to the other case, right, you go to L shell, then L shell will have 2 subshells, right. So, the subshells are designated by the letter that you have got here S, P, D, F. Now, what about the subshell? The subshells are designated by with the letter L, right. You write L. How do you write the electrons in the helium atom? You write 1s2. Where from 1 refers to what? The principal quantum number n, right. S refers to the subshell, right. S, the first subshell. The main shell and subshell are the same. So, you got 1s. The 1s state can have only 2 electrons. Why you got to have 3 electrons? If you have 3, you are violating the Pauli principle, that I will show in a few minutes time. I will show the first shell can have only 2 electrons, and so the Pauli principle should be applied to electrons everywhere. Now, many people do not understand the meaning and the importance of Pauli principle. The Pauli principle should be applied wherever you have got electrons, whether it is an atom or a molecule or a solid, whether you are talking about silicon atom or a silicon semiconductor, a solid state semiconductor. So, whether a solid or a molecule or atom, wherever you have got electrons, Pauli principle will always be found in a picture. The Pauli principle enforces certain restrictions. Whatever restriction is imposed by the Pauli principle should be taken into account, and Pauli principle is a very general principle. Wherever you have got electrons, whether electrons in atoms or molecules or solids, Pauli principle will become operable. So, you have the orbital quantum number L. So, when L is 0, you are said to be in the S state, then the P state, the D state. You talk of transition metal elements. You look at the periodic table, transition metals. When you talk of D subshell, when you got electrons ending in the D subshell, incomplete D subshell, they are called the transition metals. When you got electrons here in the S state, they are called the simple metals and transition metals and so on. Therefore, when you are talking about electronic structure of atoms or electronic configuration of atoms, we should know that for a given set of values n, L, there are 2L plus 1 values, and all these things are known to you by now. And I told you about the Pauli principle. You got the 4 quantum numbers n, L, ml, ms. They should not be having same values for a 2 different energy states. So, I will tell you once again, each and every energy state can be having a set of numbers like n, L, ml, ms. What I mean is by this is, you take the first shell. First shell means what? What is the value of n? N is 1. What is the L value? L value is 0. First shell, you got L value is 0, right. First shell means the main shell, subshell are same. So, the L value will be 0. If L is 0, ml will be 0. Okay. Therefore, what are the values that you have for the electrons in the first shell? You take the again the hydrogen atom or the helium atom. Hydrogen atom has got only 1 electron, right. Helium has got 2 electrons. How will you write the electronic configurations for the helium atom? Helium atom has got 2 electrons, right. You try to think of this kind of thing. You think of the first shell, n is 1, okay, L is 0, ml will take a value 0. What about ms? How many values will ms, how many values will it take? As I told you, ms will take 2s plus 1 values. What are the 2s plus 1 values? I showed you s is half. What is 2s plus 1? S is half means 2s is what? 2 into half is 1. 1 plus 1, 2. two values. What are the two values for ms? We showed in the previous lecture, or in this lecture also when it started. ms will have two values. What are the two values? Plus of and minus of. S is equal to half, but the magnetic spin quantum number ms will have two values, namely plus of and minus of. Therefore, for the two electrons in the helium atom, the two quantum states are 1, 0, 0 plus of. For the other electron, it is written as 1, 0, 0 minus of. This is something like distinguishing two persons. There are two S. Ramans. You got S. Raman and another S. Raman. This person comes from Chennai. Then you cannot have two S. Ramans in the class. That the teacher is getting confused. Therefore, he adds some C. C as Raman. C refers to Chennai. So, similarly now, you put C because to distinguish one person from the other person. Therefore, similarly here, you have ms here, even though n is same 1, L is 0, ml is 0, this is common for both the electrons. But ms will have plus of for one electron, minus of for the other electron. Something like you have two persons with the same initials, then same name. Then what do? You add something else to distinguish one person from the one boy from the other boy, or one girl from the other girl. Therefore, similarly here, this ms plays that role. Ms will take either plus of or minus of. Ms is plus of is a quantum state, minus of is another quantum state. That is how you cannot again write again plus of again. The third case again, I should not write 1, 0, 0 plus of, again 1, 0, 0 minus of is okay. Again I cannot write 1, 0, 0 plus of. That means you are having the same set of quantum numbers, right? So, that is not allowed. The Pauli principle says no two electrons can have the same set of quantum numbers. Very often the students make the mistake, set, the word is missing, that is a very important word. Same, you should not say no two electrons can have the same quantum numbers. Same quantum number will be there, n will be same, L will be same, ml will be same, ms should be different, right? Plus of or minus of. At least one of the numbers should be different. That is the reason why the set, the word is important. Set of quantum numbers. Now, these things are important in deciding, as I told you, the number of electrons you can have in the K shell, right? Then similarly, you go to the L shell, it will have two subshells, okay. Now, I showed that that there will be 2n square electrons in every main shell, that is what we show here. Thus for n equal to 2, that is the second shell, K shell, L shell, n equal to 2, there will be 2n square electrons. Okay, you have all these things known. So, the minimum energy condition, every system will try to keep its energy as the minimum. They are based on three basic rules. Electrons tend to occupy the lowest available energy state. Supposing you got 3 electrons, you know lithium has got 3 electrons. Will you put all the 3 electrons in the first shell? You put 2 electrons in the first shell, the third will go to the second shell. So, first try to occupy the lower energy levels. Okay. So, the lower energy levels ought to be occupied, then the electrons will go to the other higher energy levels. Let me now summarize as to what I spoke to you in this lecture so far. There are as many as 7 quantum numbers in the vector atom model. In order to distinguish one electron from the rest, at least 4 quantum numbers are required. Pauli's principle states no 2 electrons can have the same set of quantum numbers. The above factors show that there can be 2 into 12 plus 1 electrons in each subshell, and in all the main shell will have 2n square electrons. The questions which are being posed now are, how many quantum numbers are there in the vector atom model? What is Pauli exclusion principle. Last question, how does the above principle help in deciding the number of electrons that can be accommodated in a subshell and main shell? With this, we come to the end of this lecture, wherein we saw how the vector atom model or the quantum numbers associated with vector atom model in conjunction with the Pauli principle enable us to build up the periodic table or to understand the electronic configuration of atoms.